In this lecture, we will learn a lot about Monte Carlo simulation, about the different Monte Carlo techniques, different discretizations, and how to measure error associated with particular discretization technique. After this lecture, we move towards much more advanced techniques of pricing and simulating. However, we always need to start from some fundamental knowledge. Let's take a look at the closer to the content of today's lecture. First, we start with integration problems and how to calculate integrals using Monte Carlo sampling. There'll be two different approaches that I'm going to present you. A classical approach for integration, especially useful high dimensions, and integration based on expected value. Then I will show you in Python how to calculate stochastic integrals. So in today's lecture, I will spend quite some time programming and showing you how to simulate different stochastic differential equations, how to look at error, and how to analyze, and how to make your also simulation to some extent efficient. Then the third point is the discussion about the smoothness and impact of smoothness on convergence. So as you can imagine, if you have a function which is continuous and it's nicely smooth, your convergence and speed of convergence can be much better than if you consider a payoff, which is digital. This means it's not smooth, it has jumps, let's say, in a payoff function is, let's say it's digital, it's like an indicator function. Then we have to look in particular attention, we have to put some attention on how to achieve good quality results and how to monitor that. This is also I'm going to present in today's lecture. Then different types of convergence. So there are different ways of looking at your final results. Here in particular, I'll be talking about the weak and strong types of convergence. Standard error and option pricing will be discussed in next section. And then two important discretization techniques, Euler Discretization and Milstein Discretization. I will introduce those techniques and also show you how to look at the error, how to control the error depending on a time step in your simulation. So I would say this is a good starting point for being an expert in derivative pricing. I also would like to mention that already in this course, I have presented multiple times how to simulate stochastic differential equations. However, so far, I only concentrated, let's say, on a naive approach based on the Euler discretization. Today, we will learn a bit more about it, how to look also at the error, convergence, and how to improve that simulation technique. So far in this course, I have used the term Monte Carlo simulation or Monte Carlo sampling many times. In this block, I will go into details about this method and principles that you have to keep in mind once you talk about simulation, and especially if you're busy with programming. What things are you should look at? What are the important elements once you are involved in Monte Carlo simulation? Monte Carlo simulation is associated with statistical sampling. This means that around the number that we obtain from our simulation, it's a random number. This means that every time once you perform a simulation, you will get an estimate of the exact representation. Monte Carlo simulation is already a method which exists in literature for almost 90 years. It was popularized in the 30s, especially in calculation of a neutron, and also was used in the Manhattan Project. So it was very important technique. Why it was important? Because that time we could not, or the physicists were not able to perform complicated simulations. However, they were interested in some probabilistic estimates of the calculations they were doing. And for that reason, Monte Carlo simulation was very handy. Maybe a few names to mention. So it was popularized, the technique, mainly by Ulam, Fermi, Newman, and Metropolis. So as you see, it was the method origins from physicists, and is associated with a famous casino in Monaco, when the story is that where Ulam's uncle would borrow money to gamble. I'll refer you maybe to literature, Monte Carlo method in Wikipedia, that you can read a little bit more if you're interested about the history and or the initial application of the technique. Integration. So in finance, we are typically interested in expectations. Yeah? So this is what we always do. We always calculate expected value of a future payoff. So if we look at the definition of expectation of future value, so today's value of a derivative, we always talk about expected value of a future payoff, which would depend on, of course, time and a stock. Then we have some money savings account, so it could be deterministic, stochastic, and this by definition is an integral over the real axis v. We have here t s m t density of s s ds. Of course, in this setting, we assume that interest rates are constant or time dependent. This means that this integral would not depend on, so mt does not depend on s. It can be taken outside of the integral, and also in this case. But so you see that in this way, and also this is the famous CAT approach that we already have seen in the past. There's a close relation between a pricing equation and also expected value. So this is something that we already have seen. And of course, this is associated with integration. As already mentioned, Monte Carlo integration is associated with a sampling, and it is linked to probability theory. So the number, the output that we will obtain from the simulation, it's not a fixed number, but every time you repeat the simulation, the number will slightly vary. Of course, once the number varies a lot, that's not a good estimate, or this means that we're supposed to perform more sampling to get higher quality results. So this is why it's important, once we talk about Monte Carlo, to understand how to reduce the variability, the error, or the differences of how big is the variation of the final output. So this is something that I will specify, or I will give you more information in this lecture. So what I'm trying to say is that depending on the technique that you will use to simulate, you will expect higher quality or lower quality final results. This means that you could, for example, reduce number of samples in your simulation while having very high quality final result. The simulation, Monte Carlo simulation, relies on trials. So this means that if we have a density, right? So this integral could be estimated by typically sampling numbers from this distribution for stock. So we perform trying and evaluating integral for different realizations. So normally we would calculate only this integral by, let's say, trapezoidal integration or so. However, in a stochastic sense, in a probabilistic sense, this number will be based on stochastic seed, stochastic number that will be sampled. In this particular case, we will sample S, right? And we will plug into this formula to get the expected value. From an intuitive point of view, the technique relies on central limit theorem and the law of large numbers. Details on that are provided in the book. What is the biggest advantage of Monte Carlo sampling and Monte Carlo techniques, and this is also why it was used initially in already almost 100 years ago, is that the technique is very simple in the way that it can be applied simply to highly dimensional problems. So in finance, maybe we are not dealing with 50 or 100 dimensions. However, it can be also the case once we talk about the pricing of basket options. But in physics, at that time, this was the only way to get the numbers, to get the solution, given the fact that the computational power was not really existent. So let's say deterministic integration of high dimension problems could not be handled. Since the results of an experiment is a random number, so this is what I just mentioned, the error will be also having probabilistic distribution. So this is also what I mentioned a few seconds ago, is that distribution of an error we would like to control somehow. So by choosing certain settings in Monte Carlo simulation, we can control let's say the variance of the error. Of course, we would like to have the variance of the error as small as possible. This means that whenever we repeat simulation, we get a number which is very close to the exact number, and this number the output does not change so much whenever we repeat the simulation. But there are some methods how to control it and how to look at it. And we also will perform some number of simulations to show you, to illustrate how you can improve sampling and simulating with Monte Carlo. Very simple way of integration. So in this case, we have a g function. So this is function g, which is e to power x. The simplest possible way how the integration could be performed is that we sample dots in here in a cube, or actually this is a rectangular because it's a 0 to 1. We have a 0 to 4. We just perform random samples, and we count how many dots or how many samples we have under the curve. This is very simple. Just count number of samples under the curve. Then once we have number of samples under the curve, and we know the whole area, we can calculate the proportion of the samples which are under the curve, and that will be good estimate of the integral. I will show you later in the code how to perform this simulation and how to see the convergence, but this is one of the simplest ways of how to perform simulation to obtain integral, estimate of an integral. This type of integration we are not going to use in finance. However, it could be used if we have a very complicated, highly dimensional problem. So as you can see, in this case, it was very intuitive, right? Because we just count all these dots. We check how many of them are actually, given the whole population of dots, how many of them are under the curve. That gives us the probability being under the curve. And then if we calculate the whole area of this rectangle multiplied by probability of being under the curve, that's an estimate of the integral. But that will be clear in a few minutes once we talk about simulation. Okay, this is the first and very straightforward approach to calculate expected, or maybe necessarily expected value, but the integral once we have a deterministic curve. So you see here what we do, we had a problem which is not really stochastic. So in pricing, we have an expectation of future payoffs where we have a stock which is stochastic. So obviously that naturally fits that we simulate a stock price and then we use that estimate, we use that samples to calculate the value of a derivative. In this case, we have a problem where the function that we are interested to integrate has nothing stochastic inside. It's just deterministic function over 0, 1. However, using the Monte Carlo technique, we can make it essentially stochastic. Solution is stochastic. However, the function itself was purely deterministic. The limitation of this method, as you can imagine already here, is that, okay, if we know the area of that we are interested to integrate 0, 1, so it's easy, 0, 1. However, how would you choose how high this domain should be? Because 0, 1 is the limit that we have chosen here, but how high this rectangle should be. So this means that you should know something more about the function, because if this function, for example, would start, let's say here, but it would be like this rectangle would not be big enough to handle the samples, because there are no samples here, there are no samples outside. So this is something to additional, let's say, disadvantage of this technique. However, if you know some properties of this function, like you know where is the maximum, minimum, that could give you better understanding how to build this rectangle. On the other hand, here we see that it was not maybe the smartest idea how I have done here, because it was maybe more efficient to do it rectangle of this shape, right? So we have this area. So forget about completely about this part and focus only on this part. What would the benefit of that is that you see that sampling in this area does not bring anything into our result, does not improve convergence. It only costs us time, because those samples, they are not really contributing. However, if you are here in this domain, every sample, whether it is above or below, it really helps. But here, I would say it doesn't really help. So we can easily reduce the area from 0, 1 to 0, about 2.5, 2.6, and we will have very likely the same quality of results. However, we could perform much faster the simulation. So that's something to keep in mind. Of course, once we talk about this type of integration, this is more appropriate once we talk about high dimensions. So one possible idea would be that we are choosing a random point G, so it's a G hat, in a whole domain, that we are just one, let's say, sample for one point xi, yi, and z I. And then we multiply this point with the whole area of this area, right? So we multiply for whole omega. That would be very rough estimate of this integral. However, sometimes if you don't have anything, that kind of estimate could be enough, especially if we have a very high dimension. However, this is not something that we are going to use into pricing. That will be very problematic, especially that our numbers that we obtain, it would be highly inaccurate. Here I provided more details on this technique that you could implement, of course, and use. However, it's very unlikely you'll be using this technique in finance. Typically in finance, once the problem becomes too computationally intensive, it is not really common to apply the technique. So if we would price a basket of options, and each of these options would require multi-dimensional stochastic differential equation and will be heavy simulation, typically industry standard would be to simplify, for example, by not taking smile or skew into account. And this is typically motivated by efficiency and also time that is necessary to calculate. So this is something to keep in mind. Maybe one more element here is that the expected error is reduced by factor square root of n, so n should be very large. Of course, once we have those kind of simulations, and also here, in order to get a good estimate of this integral, we need to perform many simulations, many samples. So that's not really efficient way of performing this kind of calculations. This is also here some simulation. In a few minutes, we'll go to Python code that I have prepared. So here's the result. So here we have few elements. So we have a number of samples. So it's n's 10, 100, or 10,000, and so on. So until 10 million. Here is the comparison with the exact solution in here. So we see the error here, and this is time needed to for this calculation. So you see that if you have here, this is 1,000 samples, the error is still rather big. It goes immediately much smaller once we add tenfold. So it's 100,000 samples. That becomes much better. But it's for a low number of samples, it's not really performing very well. Here's additional observation that in order to get a quality of 10 to minus 5, I would say, which is not really extremely high accuracy, then we need about 10 million samples for integration from 0 to 1. So you see that's highly demanding computational technique. On the other hand, we can perform integration of the deterministic function using our expectation approach that we have seen already in the pricing. So maybe it's not so straightforward how to link this integral here and the expectation on the right-hand side. But to illustrate what's the relation, let's just go here. We don't need too much space. So let's write an expectation. First, we start with an expectation. So we have an expectation of a function g of x. And we have a random variable that we're interested in. So x is a uniform on a and b. So this expectation, it will be given integral from a to b. So this is this expectation only. I don't include this b minus a, keep in mind. So this expectation is equal to integral from a to b. And then we have g of x times the density of x. So we have a uniform distribution here, right? So density of a uniform over interval a to b, it is 1 over b minus a. And we have here dx. So you see this is constant. We can take it outside. So in order to get rid of it, we have to multiply both sides by b minus a. And then if we multiply b minus a, you see that this element will cancel with this. So we have exactly the integral on the left-hand side. So you see this is very nice, very elegant connection between sampling from uniform distribution, uniform samples on some area, and calculation of integral. And of course, how to perform sampling, we just calculate the expectation is average. So we calculate average of values of function g at the samples from uniform. And then we have, of course, 1 over n, which is the number of samples. So it's average. Basically, this whole term is average times b minus a, which is this term. How do you think? Which of this technique is more efficient and more accurate for a given number of samples? So this is something that we will test in a minute. Here's a little bit of relation to the law of large numbers that we have for xi's that are independent random variables, identically distributed. Then we have the following connection. We have for n going to infinity, the average converges to this integral, which is expectation, right? So this integral is an expectation of random variable x. And xi's are independent samples you can think of x. And for the variance, so this is the estimation for the variance, we have 1 over n, so this is can go outside. And then we can also, so if we have samples, we can also calculate estimate for the variance. Unbiased estimator, maybe you know from statistics, is that it's slightly different. We need to have n-1 samples. The weight of our summation has to be with n-1. So this is important measure of the variance, and here we have the mean. So this is our, let's say, mu bar, the estimate for the mean. Okay, so here's the comparison of the naive approach, so the one that we sampled in the rectangular points, and then we check how many points are beneath the curve. And this is the stochastic approach where we calculate expectation. As you can see, I changed a little bit here the a and b's, so that it's actually, we have from 0 to 1. Actually, this is the same a and b. Yeah, so it's a 0, 1, so it's exactly the same function. And here is the comparison. So this is the naive approach, this is the expectation approach. And you see that already for 10 to minus, so for 10 samples, here this error is much smaller than this one. This is uncomparable. For this is 1,000 samples, we have 14. This is already 10 to minus 3. So it's a big improvement compared to the standard approach. Time-wise, I see there is improvement. However, it's not so dramatic as we can see in accuracy. So getting 10 to minus here is 4. This is 10 to minus 3. So it's always an order better and 3 times, let's say around 3 times faster. Let us take a look now at the code. So I would like to illustrate how to perform this simulation. So you see it's very, the code is very simple. Here, this is the main part of the code. We choose number of samples. This is the cube, the rectangle that we choose. So it's it's a 0, b is 1, and then we have a c and d. So this is the lower limit is 0, and d is 3. These are the settings. We integrate function exponent of x, and we call function compute integral 1. Compute integral 1 is here. So how I have done it is that first we sample points xi, so from axis from a to b, this is the random points, uniform points on axis from a to b. And for each of those points, we sample also uniforms from C to D. So basically you have a pen. You can construct a grid that if you plot xi versus yi, then you get a grid of points. Then what we do, we calculate points pi. So we check which of those samples that we have is smaller than function g at that particular point. So you see, this is what we do here. So this is function g at xi, so at each point on the axis x, and we check whether it's bigger than a point yi, which is a sample on the other direction. And this is an estimate if we just sum it and not divide by number of samples, or we simply calculate the average. This gives us the probability of being under the curve that we have plotted. So this function g, this probability of being under the curve. And then to get integral, of course, we need to take probability, so proportion of the whole space, we have to multiply with the area, which is simply rectangular. And for the other approach, we have we again sample from uniforms A and B, and we calculate average or mean of g of xi and multiply by b minus a. So this is what we have seen already in the slides. Only one thing to keep in mind is that, look, in this approach, we have 2 points that we need to specify. So this is something that you would expect if somebody asks you to perform integration. normally you would be asked, okay, integrate function from a to b. In this approach, we not only need to specify the area a and b, but we also need to provide a range for values of the function c and d. So this is obviously that's a significant a limitation. Okay, once we have that, we perform the second integration, you see only with 2 arguments, and then we plot some outputs. So let's run the code. Here are some, this is some information. So the first integral value from first integral, 0.77, second integral, 0.76, and this is analytical expression. And here you can see the curve versus the samples. Let me do more samples. So it's we can look at the convergence. Right now we can see there is not too much difference between the two. I would say even the first approach is better. Of course, you can see that it changes a lot, right? So this is related to the error that we have in the simulation. So you see, I just repeated once, and this result rather be stayed close to our exact solution. However, this result here, it's worsened. It's moved really significantly. Let's do it again. Oh, it's the same again. So the second approach, the variance of the error is much smaller than the first approach. You can see it moved really significantly down right now. Now it's very close. Now it's very much lower. Again, close. Again, lower, and so on. So you see there is the variance of the error for the first approach is significantly higher than the other approach. Of course, if we do this d function in a d limit, if we make it, let's say, 15, so the space of our, so we have this rectangular here, but we increase from 3 to 15, so it's much bigger rectangular, and lot of information which is not going to be useful. If we integrate that, you see it's also much worse than before. So it's we essentially lose much more computational effort for the area where the function doesn't really is plotted. So you see before the lowest was 0.6, now it's 0.5, 0.7, 0.8, 0.3 even. You see, so it's 20, more than 20% off. So let's leave it like we had. So we have a upper limit for the rectangular shape. Here's 3. Now let's also try to increase number of samples. So then we can see that there's an improvement in convergence. In finance, we have to deal with stochastic integrals on a daily basis. There are different types of stochastic integrals. In this part, I would like to bring you some possible examples of integrations that you may encounter. Here we have a case where we have a Brownian motion, WT. This is the blue line that it's a Brownian noise. And then we have 2 integrals. The first integral represents, you can think of a running summation. So every additional element every time, it will be summation until that moment. So if you look at the red line, essentially it constitutes the summation of blue line until this moment, and so on. So you see, we have basically Brownian motion times the dt, or ds in this case. Another type of integral is that we sum Brownian motion, but on the increments of the Brownian motion. So this is, you see that there is a big difference between the two, and also in you can see in a variation of the paths. So we have a blue line, which is just the Brownian motion. We have a red line, which is very much smoothed out, and this is due to this element of ds. So essentially here you can see that we are summing Brownian motion, and this sum, this red line, represents a sum of all the history of Brownian motions until this moment. So obviously, if we are at this point and we sum that extra element and multiply with a dt, this is not going to be moving a lot as the Brownian motion itself. And the last type of integral is when we sum Brownian motion, but we multiply with the increments of Brownian motion too. So this is kind of similar to this case, except that here we have a dt or dt in terms of time step, and here we have increments of a Brownian motion. Those are typical examples. Now let's go further to more concrete cases and how to solve them. So imagine a scenario where we have a function gt, which is something that we have seen in the figure before, with integral from 0 to capital T. and we have here some function gs dws. This function gs in general could be stochastic, but here we would consider just to be deterministic. How to solve this type of integral numerically? You would do the following. You would first define a partition, and then, as in the ethos lemma, you just approximate this integral as the summation over all the terms times the increment of Brownian motion. So this is this part will be discretized into this difference between these two Brownian motions times the product. Note what is very important. This is ito integral. So we are the function gt is evaluated in the beginning of the interval. So if you have a grid, this is tk plus 1, function g is always evaluated at this point. So it's a g, t, k, and then we multiply by this whole interval. If you have a middle, for example, point, so you would choose not point gtk, but gtk plus 1 plus tk divided by 2. So if you'd consider function tk plus 1 plus tk divided by 2, that would be different type of integral. That's called Stratonovich integral. But in Ito case, we always choose the left-hand side, the left boundary. This is in particular important because it's very handy once we talk about independent increments. So that facilitates a lot of flexibility once we would like to derive something analytically. Computationally, it is not so much big difference. Okay, so once we have those expressions, here, let me just erase here, make some space. So if we discretize those terms, we can simply calculate this integral, and then we can compute expectation and variance. In this case, if we have a gt function, which is deterministic, we know that the whole this expression is going to follow normal distribution, because essentially what we are doing, we are summing independent random variables, normally distributed random variables. So sum of normals is also normally distributed, and there is some scaling coefficient. So let us consider an example. When we have a gt function equal to t squared, we choose time horizon to 1. And of course, we can solve those expressions analytically, because here we have expectation, of course, expectation, everything related to Brownian motion, because it's independent increments. If we will think of a summation, this will be just 0 to the property of Ito integral. And once we talk about the variance, we need to look at the following term, where we have expectation of 1 to power 1 t squared. So actually here we would use the Ito's isometry, which gives us t squared dt. So Ito's isometry is the property that we have used to evaluate this integral. And if it's integration from 0 to 1, so we have 1 t to power 4, we can simply find out that this is 0.2. Let's try to simulate this in Python and see how our results will converge to these results. So it's 0 and 0.2. Keep that in mind. Okay, here's the Python code. Just double check. Yes. So here we define, again, we have two blocks. So here is the block where we call, when we specify the configuration. So here we have number of paths, number of steps. So number of paths for Brownian motion, of course, number of steps, this is the discretization. Time horizon, we have a function, it's a lambda function, t squared, this is what we have here. And for the computation of integral, again, we define random numbers, so it's independent increments. Integral and the w, those are just empty matrices. We have some running time argument, dt, so depending on number of time steps, the different delta t, essentially. This is element part where we standardize random numbers, so we always make sure that there is a mean 0 and variance 1. In the first step, we define Brownian motion, so you see it's a next element of Brownian motion is the previous one plus the increment is plus dt or square root of dt times the independent increment. So this is how we construct Brownian motion. And once we talk about integral, we just sum over all the elements. So you see I1 is equal to previous element. So I1 at I plus 1 is equal to I1 at I. And then we have a sum of a function evaluated at time ti and time ti, you see it is running here. So we start with 0, and every time we just add dt. So it's kind of, we monitor how far we are in time, and time the Brownian motion increment. This part, of course, it is maybe, it's clear how it's done here. Obviously, you could replace this wi plus 1 minus wi simply by the expression that we would just do here, right? So if we wi plus 1 minus wi, this will be just this expression here. So this is something to keep in mind. I did it maybe not so much efficient here, but it's clear how you first generate Brownian motion, or first generate random noises, use those noises to generate Brownian motion, and then use Brownian motion to construct a process. In this case, we define the integral. So okay, let's run it. Okay, so here what we see, here we have a distribution. So this is our integral at time capital time t, capital time t1. This is the distribution. As we discussed, sum of normals follows normal distribution. So here we have also, this is normally distributed, and mean is 0. You see 10 to minus 17. And this is due to the fact that we have scaled our, we made sure that our noises follow normal distribution 0, 1. In a second, I will remove this constraint. We will see what will be the impact of that. And the variance, you see, it's a 0. Exact was 0.2. Now we have a 0.04. Let's try to remove the condition here. So we remove the part where we do the scaling. So as you remember, please keep in mind, we have on 10 to minus 17. Now, without scaling, we have, you see, expectation is not anymore 0 or 10 to minus 17. It is 10 to minus, in this case, it's 10 to minus 3. So we, of course, maybe the variance you can see is actually improved, but it's not what we would normally expect. Let's run it again. So you see, mean is far away from 0, further away from 0, and then variance also deteriorated. So it's this condition where we do the scaling, where we make sure that if we would like to sample from a normal distribution, and we do many samples, always check whether the samples, you can scale them such that they will fit the properties that you know about distribution, that you make sure that your samples follow that property. So in essence, you can say, if we have a distribution, we make samples. By scaling, you essentially impose conditions or properties that you know that your distribution should satisfy. So for example, mean and variance. So this is what we do here. We impose those conditions on the samples. Okay, let's go back to our slides, where we continue with the different type of integration. So another integration that we have seen in the initial figure was integration where we have a Brownian motion times the Brownian motion increment. So we also see here that the expectations will be simply 0, because as you remember, we do ethos integral. So if we discretize this summation, we will have here WTI. Sorry, I should do it slightly differently. Yeah, I should first write here, we have time ti. Here will be ti plus 1. Then we have here, we would have a WTI. And then we multiply, so this will be this term. We multiply this term by whole increment, which would be here WTI plus 1 minus WTI. So you see that this term and those are independent, because they are not overlapping intersections, so they are not intersecting. So this means that they are independent, and Brownian motion has property of independent increments. So that's the construction here. This integral actually it's much more complicated than what we have seen before. It's not so easy to solve this integral. To do that, we have to follow a little bit of a trick, and this trick involves ethos lem. Those type of integrals, when you have a Brownian motion and you have you integrate something with respect to Brownian motion, often you have to apply ethos lemma. So this is something to keep in mind. Let me make some space here. That will be handy in a second. So you see that here we have the WS, and we have some increments, right? That suggests essentially, so we have this again time TI, TA plus 1. We have this part multiplied by the value at the end. Maybe that could be a little bit of intuition. But at the end, what we have to do, we have to consider function x squared. So you can see we have a Brownian motion, that we have two Brownian motions. You can maybe get inspired that the guess that you should have to apply to Ito's lemma, it is x squared. Unfortunately, for Ito's lemma, it is often a little bit of experience and sometimes a little bit of guessing what type of function you should use in order to obtain what you want to obtain. And this is what will be very clear in a second. So if we apply Ito's lemma to x, actually what we are doing, our x process, it is considered to be Brownian motion. This is what we want to do. And now we want to find out function, the dynamics of function, which is equal to dw squared t. This is our objective. So by applying Ito's lemma, this is our result. So I'm not going through the details. This is already what I was presented previously. But once you substitute, use f equal to wt, this is what we end up with. You see that we have a dw squared, and here we have a term which is 2 times wt dwt. And you see that this term here, so let me mark it here, it resembles the term that we have here. So by applying Ito's lemma to x squared, we have derived actually something that we are very much interested in. So if I would integrate this term here, this will be also integral here, of course integral here, and here, then you see that this term would resemble the term that we have here. And this is what we are doing next. So by the integration, we end up with the following expression. So this is, of course, dwt squared integral, obviously it's a w squared capital T minus w squared 0 equal 2 times this integral plus t. So of course, now we can easily find out that this term is here. So we know the solution for this integral, it is half wt w squared t minus half of a t. So this is something to keep in mind, that often application of Ito's lemma allows us to compute those stochastic integrals. Like I mentioned, often you have to have a little bit of experience to think what type of function you have to apply to make it to happen. And also one more final remark, this term that you would normally, if you just do normal integration, this term wouldn't be there. This is related to Ito's integral. So here is what we would obtain once we do discretization. So again, we do like we did before, independent increments, and we can also calculate this integral now theoretically. We know it's we can calculate at least the expectation in the variance. I'm not stating here what the distribution of it is, because we know that we are having wt squared. So this integral is a wt squared. We can actually see that this is some kind of, here's a scaling coefficient, scaling. Now we have also transition of the distribution. And of course, once we have a normal distribution which is squared, then we have to deal with a high squared distribution. So then we can still calculate expectation on the variance, but it's not anymore normal distribution. Let's take a look at the code. So now we have to change our code slightly. So we have, of course, now let me check. In our integration, we were doing integral to t. So let's go back here for a second. So you see that we are doing t equals to 2, and then expectation is 0, and variance is equal to 2. So this is something to keep in mind. Let's go back to Python. So with t is equal to 2, what I will do next, I will define function g to be equal to t. So if I have a g of t equals to t, so this is what our intention is. And here what I will do is that here we have a g of time, and here I will do g of w, and here we will do something like this. So as you can see, this expression here will evaluate, it will be equal to w at time ti. This is our intention. So you see, just one line of change, and we can switch between these two integrals. If I'll evaluate this term, you can see that this distribution, indeed, it's not normal. It's far away from normal. It's not symmetric. It is actually high square distribution, and we see here mean and variance. So variance was in our slides also around 2, actually exactly 2. For mean was 0. Let's see whether we can improve that by increasing number of samples. So now I have 100,000 samples. It takes quite some time. Let's give it a few more seconds. Yes, this is quite some iterations here, because we have 100,000 samples plus 1,000 time steps. So it's a plenty of steps, but we are done. So those matrices that we had to deal with, they're rather large. But this computer, although not so new, managed to do that. We have a mean equal to 10 to minus 3, and we have a variance. Variance actually deteriorated slightly. What is important once we do Monte Carlo and we talk about convergence, it is also important that the random number generator that is used to generate those numbers, it's also good quality. I think NumPy does not have anything special, so it's just a standard algorithm. But I know for the fact that by changing numerical routines, so algorithms that are used to generate random samples, may significantly improve the convergence. But this is what we cannot really observe here. This is not the scope of this course. Okay, let's take a look back at the slides. Final experiment and final discussion will be about ethos lemma. Maybe you remember we had this famous ethos table where we had dt, dwt, and we had on the other side dt, correct here, dt, dwt, and we have this term. So everyone remembers. This maybe not the sorry, this is not the nicest table, but let's see. So this is 0, this is 0, this is 0, and here we have dt. So now let's try to understand or try to explain why this term here it is 0. So what we will do, we will work with a product dwt. So first of all, let's take a look at expectation. Expectation of dwt squared, because we have a product of these two. In essence, we can consider as a limit of delta t going to 0 of the discretized Brownian motion. We know that expectation of this term to be basically just a time. So so actually it's a variance, so it's a dt. So we know that expectation of a dwt squared is dt. This is a rather heuristic approach to explain to us. If we look on the variance, we follow exactly the same steps. So first, limit dt going to 0, increments. It's of course we have a variance to power 2, so it's equal to expectation of a Brownian motion, the increments of Brownian motion to power 4. This has to do with the fact that we have an expectation of increments will be 0. So then we end up with only fourth moment, essentially of a Brownian motion. And now if we just continue derivations, we can decompose these expectations of a square of expectations. So it's expectation to power 4. This is equal to the square of expectation of the second moment. And if you do a little bit of algebra, you can find out that the variance in the limit is basically 2 times dt squared. From this result, so we have a dt here and we have a 2 times dt squared, we can conclude that the variance converges to 0 much faster than the expectation when dt goes to 0. And this is because of this, we essentially have this rule where we say dwt squared is equal to dt. So this is a rather heuristic approach without going into the proof, theoretical proof, which is rather involved. But I think that kind of gives you intuition why dwt is equal to 0. So essentially, variance goes to 0 much faster if we decrease the grid size compared to the d theta. And this is what you can also see in this experiment here. I'm not going to go through the code. The code is available in the book. So here what we are doing here, we are, m is the time step. So how many, for given grid, how many terms we would have, how many divisions we will have of our grid. So we make it smaller and smaller. The grid size, and the blue line is the expectation. So the expectation goes to 0 much slower than the variance. Variance converges much faster. You see 25, variance is literally 0, and the expectation is still high. So this is the interpretation that you can think of. And I think having this picture in mind, in this figure in mind, would explain to you why we have the expectation and the variance, what goes faster to 0. This is something that worth to keep in mind. In the previous examples, we have seen the relation between convergence, so in terms of an expectation and a variance, in the relation with number of Monte Carlo paths. Now we will investigate that further. For that reason, we will consider two functions, function g1 and g2. As you can see, they are very similar functions. So g1 is indicator. For x bigger than 0, it is 1. For x smaller than 0, is 0. And for the function g2, I have chosen a normal CDF. So essentially, you can see this is for 0. If this is 0 here, function, the first function will be just here 0. Here we have 1. And the second function, it is a CDF. So it's essentially functions just like this. So there are two very similar functions. So they both have limits of 0 for x going to minus infinity and 1 for x going to plus infinity. And now we will investigate the expectation of each of those functions. So you can see expectation of gi of the Brownian motion at time ti, at time t equal to 1. This is what we see. So we have a t equal to 1. And so we sample Brownian motions, and then for given Brownian motions, so Brownian motion at the given time t equal to 1, we calculate the expectation. And now we will see how this error will change depending whether for increasing number of simulated samples, what is the error for a smooth and non-smooth function. So this is non-smooth, this is smooth function. Theoretically, we can prove that that's rather easy, that in both cases, so we have expectation for function g1 and g2, we always have half. So for both cases, we have half. So it's an integral of the indicator function times the density. And we know this will be a density of 0, 1, because we have a variance of 1 for time equal to 1. So you see this will be integral, half of the integral from 0 to infinity of a normal PDF, that's half. And for the second case, we end up with, you see that we have a density x dx, which is equal to df. I think this is, maybe I can refresh that df dx is equal to f of x. So then this means that we have df is equal to f of x dx. This is what we have here in this case. So this means this df will be here. And this is equal to half of f squared. So it's a CDF squared from minus infinity, and here we have limit of plus infinity. And this is also equal to half. So let's take a look. What is the impact if we increase number of paths? Can we actually see the improvement in the convergence? So again, so this is a picture here on the left-hand side. So we have a digital function g1, and we have a very nicely smooth function for the CDF for g2. In both cases, integrals will be equal to, the expectations will be equal to half. So what we do first, we define error function. So error function, depending on number of samples, is equal to value of estimated from Monte Carlo. You can see it's estimated as expectation over all number of samples. So this is number of samples. And here we calculate value of at particular sample from Brownian motion at time j, right? So actually this is a sample j. The I corresponds to function number. So it's for first function, we have a 1 here, number of samples, and then we calculate the average. And the error will be the difference between, of course, here is in both cases, it's equal to half, right? So we calculate the difference of the two. And you can see that in this graph, we show the error and we compare to the number of samples. So from different number of samples, we report errors. And you can see for the first function, it's kind of oscillating with a rather wide range. So this is the range for blue line, which corresponds to the non-smooth case. and indeed actually it converges. You can see some convergence here, right? But it's rather slow. For the red curve, you see that convergence, it's much faster. So it's you can actually see in this case here. So it's a big difference. So maybe you have so if you think of implementation, you have constructed a generic code which allows you to price both functions almost the same. They have very similar properties. However, one function is not smooth, another one is smooth. You can see that your results, your convergence, may depend on number of samples. So it's depending on the payoff, you may expect sometimes different convergence results, especially for the cases where we have to deal with functions which are not really smooth. And that's something to keep in mind. This is particularly important, so especially this blue curve, once we talk about the digital type of payoffs. So those are also very popular payoffs, which you can imagine as follows. There is a counterparty which buys a derivative, which states if value of a stock will be bigger, let's say, than zero, then or zero maybe is not so realistic because stocks are always bigger than zero except for the default. But suppose here is 100. So if your stock will be equal to 100, you receive $100. But if your stock will be lower than 100, then you receive zero. So you see that in a call option case, you had always this smooth transition. So there was a strike, stock, and strike, and you were always you were receiving the difference between the two. In this case, it is basically whatever it happens, you have a strike. So it is basically very digital. So we could say we could receive 100 only in the case when the stock at the maturity is bigger than some strike. And that's obviously a digital type of payoff. For a call option, we will have maximum of ST minus K0. So this is much smoother compared to this case, right? So then the results of the converged results, definitely you would expect worse results than for simple call or put option. So this is something to keep in mind. If you have a payoff which has some digital features, this is always very much alarming because this means that very likely you will have a problem with simulation, especially if you don't want to have many samples, you would like to have maybe few realizations. Then you can see that errors, in this case, if you compare the two, could be even 3-4 times bigger errors. So if you have a payoff which instead of 100 here would be 1,000,000, this would be substantial difference in your evaluation. So please always keep that in mind. If we talk about Monte Carlo simulation, it is also very important to talk about convergence. In finance, we are mainly focused on two types of convergence, a weak and strong sense. So let's take a look. So suppose we have a variable xt and we have approximation xm. So xm is indicating number, m indicates number of samples. So xm approximates xt. If we have this approximation, we can define weak and strong convergence. Strong, which is the strong, it means it's much more powerful than weak. Once we have a strong convergence, weak convergence also is implied. So let's take a look at the definition. The weak convergence, here the error would be defined by expectation under some measure of absolute differences of two quantities, samples that we have generated to approximate variable x and variable x. So you can see that this expectation here, we are looking at the difference at the sample level. So this is very important. And then we have, of course, depending on the difference, what we have there, we can quantify whether the error is in h alpha, order of h alpha. And h will define here the discretization, the time step, what is the time step in our discretization scheme for achieving of xm. On the other hand, the weak convergence is when we talk about also absolute sense, but you see this time we have expectation which is not outside the absolute value, but this is inside the absolute value. So now we talk about a difference of expectations in absolute sense, and this is weak convergence. How to think about it? I will give you a small example. Suppose we have a variable So we have our approximation xm, which has three realizations as first realization. So it will be let's do it. xm1 is 1. We have xm2 is 2. xm3 is equal to 3. So you see that we at point m, so the final time step, we have three paths. We have a path with value 1, 2, and 3. And then we also have exact representation at time t. So then we have the following. We have for the first case, we have a 0.5. For the last case, we have also 0.5. And for the second case, we have 5. So let's take a look. So we start with the weak convergence. Weak convergence, it means we take expectation of the first function. So let's define our function g equal to just xm. So essentially, we are just looking at the expectation of xm. So then we have expectation of xm. In this case, we have a 3, 5, 6. So we have a 2. Right? The expectation, let me write maybe nicely here. Expectation of xm is equal to 2. On the other hand, if we have a second variable, so we look at the expectation of xt, we see that we have a 5 and halves. It's also 6 divided by 3. We also have 2. So you see that there is basically no error. So obviously this performs very, very well. So there is no error in a weak sense. The expectations are exactly the same. However, if we look carefully, those are different numbers. So although the expectations now match nicely, we have to deal with something which is completely different. They don't really match because the first part in approximation we had 1, in exact representation we had half. For the second part we have 2 versus 5, and the third one we had 3 versus half. So you see, although at the path levels we have something which completely doesn't match, overall, if you look at the means, then we have a nice match. So obviously we can see that this is nicely convergent in a weak sense, but definitely is not convergent in a strong sense. And this is often the most important path. So once you talk about convergence on the path level, then we talk about strong convergence. If we talk about convergence in a weak level, on the expectation level, at the moment level, then we talk about the weak convergence. So this is something to keep in mind. There's always big difference. If you develop an approximation of a model and you say that you have a strong convergence, that's extremely powerful tool. This is basically means you are almost accurate at the path level. It's very good. If you talk about weak convergence, typically then you only have moments which are nicely matched. If you would have an approximation that is used for, let's say, exotic path-dependent payoff, then weak convergence would not be enough. Then you need to have strong convergence, because path dependence means you need to have your payoff could really depend on those numbers. And then you need to have a strong convergence. So this is very important, and please keep that in mind. Given all the information so far, let us construct a complete Monte Carlo pricing algorithm. We always start, this is the most important, we always start with a pricing equation. It's either a time-dependent or path-dependent payoff, or we have a European type. In this case, we consider European type. We always have also a driver, stochastic driver, for a stock or other asset of interest. This asset is going to be used in evaluation of the pricing equation. Normally, we cannot evaluate this expectation in a closed form, and typically this is related to the fact that the stock dynamics, stock process is too involved, and for that we need to perform Monte Carlo simulation. Okay, so the pricing algorithm, Monte Carlo algorithm, will look as follows. First of all, we have to define a grid. A grid typically would start from time t0, so this is from today, until time tm, or capital time T, until the payment of the contract. Of course, if your contract will have multiple payments, you have to make sure that those dates will be also on this grid. So this is kind of a virtual grid you can imagine from t0 until t. Typically is equally spaced, so delta t is fixed. However, it can also happen that some people, in some occasions, you may consider grid which is not equally distant. This is maybe more into PDE approach, not in Monte Carlo. Monte Carlo standard approach is to have time steps equally distant. However, if you have, for example, Bermudian option, which has payments at a specified date, and you have an algorithm which allows you for a big time step simulation, so this is something that we will discuss in next lecture, then indeed you may remove the intermediate steps. Then indeed you would like to concentrate only on the important pricing dates. Of course, once you consider a case where you have more steps, then indeed your accuracy increases. But this is sometimes we talk about, this is why we talk about exact simulation or Monte Carlo simulation, which allows for big steps. So as you can imagine, there are Monte Carlo methods. This is something that we are going to discuss next time, that allow you to neglect small time steps. You can make big time steps while keeping accuracy at the high level. So this is something to keep in mind. If you have a standard approach that we are going to discuss today, the more time steps you have, better the accuracy. However, it is always a cost of time that you have to pay to simulate. So it's longer it takes to simulate. Once you have more advanced techniques, or you have closed form solutions for making large Monte Carlo steps, that's always beneficial, especially in accuracy and also time. So first we define the grid. We have an asset which has a Sij, so we have two indices. The first index is a time index. The second index is a path number index. And we have a payoff. Payoff is Hj, so you can see J also value of a payoff depends on path number. So we have a second index is a path number, and we have a payoff which also would depend on a path number. So we have a, let's say, n number of payoffs, and then we calculate average essentially of that. So if we have a European type option, you see that payoff will depend on S and J. So this means we only consider, this will be time here, Tm, we only consider paths at this point. And this is why we have a final state. If we have a path-dependent payoff, so the payoff which involves intermediate payments, or we observe something how path behaves in time, then you see that we don't have any more m, we have a whole index. So we need to observe how path behaves in time. Once we have that, so whether we have a path-dependent or let's say European type of payoff, then we can perform. We can go further in the next steps. In this case, we consider. I would like to concentrate on European type payoff. Continuum, or let's say path-dependent payoffs, we will discuss later in this course. But at this point, it will be too complicated to talk about conditional sampling or those kind of elements. Are not so much important at this point. So now we have expectation under Q measure. Of course, we have to make sure always that our process is defined under reasonable measure. We have a payoff. As you can see, right now we don't assume anything about interest rates. This, however, would also work in an interest rate case once we have a stochastic or deterministic interest rates. So then we approximate this expectation as the average of from j equal to 1, from 1 until n. So for every payoff which we evaluated for path, we take average of that. And this is hn bar. And once we have that, we can calculate option price. So we see that first we had an expectation, and now we have a discounting part which comes outside. So in this case, actually, we have chosen to be interest rate to be deterministic. Actually, it's a constant interest rate. However, we could also generalize it in a case where this expectation also could involve interest rates. But you can see now it's a part where we say we calculate with Monte Carlo a payoff, expected value of a future payment, and then we discount it. So it's always two steps. Value in the future, discounted to today. It complicates it slightly once we have stochastic interest rates, because you cannot really separate them, especially if interest rates are correlated with your asset. But in this case, we can just separate. We say future expected value, discounted to today. And once we have that, once we have an approximation of our payoff, because this is an approximation because we perform a sampling, then we can determine the standard error, which is defined in the next slide. Once we compute an expectation of our payoff, this expectation or the average from samples, it may vary. So whenever we will repeat the simulation, numbers that we obtain could be slightly different. To measure how much error is in that variability, depending on number of paths, it is actually definition of a standard error that we will discuss now. So to go into details of standard error, we need to have two ingredients: expectation, which is here in this point. We have a expectation is a rather easy part because by strong law of large numbers, we know that as number of samples increases, our average converges to the theoretical expected value with probability of 1. Now, we need to also compute the variance of our mean. So this means that if we repeat our simulation, our expected value, mean, is not a number, it is a random variable. And this random variable has certain distribution, which has a mean, essentially we can see in of average, and also it has a variance. And so of course, ideally, we would like to know that this variance is as small as possible. This means that whenever we repeat the pricing, the number that we obtain will be very much stable. So for that, we need to also compute the variance of the mean. This is, a mean is computed from samples. So this is a second ingredient. The first one is the expectation. We know that converges, if we have number of samples increasing to infinity, it converges in probability 1 to the theoretical value. And now we also need to have a variance. Variance of the mean, we substitute here, you see, it's a bar, so it's a samples mean. We substitute the definition that we have from previous slide, and then we just assume that we have samples which are drawn independently. This means that we can exchange variance of a sum with sum of variances, and this will be basically approximated by the variance. So you see it's n is gone because it will be n times, and we have a variance of the payoff. So once we talk about the variance of the samples that we have, the unbiased estimator of the variance of the mean is computed as follows. So we have 1 over n minus 1, so n is number of samples. And then we have just a definition. We have a payoff evaluated at each path minus the average. And of course, this is quantity that we have to compute once we have performed the experiment of computing the expectation. And then definition of the standard error, so the error that actually we are interested in, how much variability is our expectation given a certain number of paths, is proven to be of the following, is actually defined, this actually is known that in asymptotically in convergence to the following quantity, we have a variance which we, or standard deviation that we compute from this expression, divided by square root of n, which is number of paths. So essentially, if you would like to measure the error, the stability of your final results once we perform pricing, you have to calculate a payoff at each path minus the average that we have obtained from the paths, and then you have to divide the result, the variance, you have to take a square root and divide it by square root of n. From here, actually, we can conclude that when the number of samples increases by a factor of 4, the error reduces by a factor of 2. So this is how you can think how, by increasing, if you see an error, how much more paths you have to add in your simulation to reduce the error by 2. So it's always factor of 4 to reduce error by 2. If you have a pricing problem that involves multiple dimensions and you run extremely large number of paths, that could be, of course, the cost that you will have. It would be computational time necessary for the evaluation. So this is not always ideal. But understanding how big the error is, it's very crucial, because once you have the error, the standard error, you can also think of a confidence interval. Then if you have confidence interval, what is the worst, the highest price, what is the lowest price that you may expect, then essentially that spread, the difference between max and mean, you can think of including in the overall price that you will sell your derivative. So basically you can perform some kind of estimate, what is the worst case scenario, and then that difference include in the price of derivative, just to make sure that that you don't suffer from insufficient number of Monte Carlo paths. Classical way to simulate stochastic differential equations is via Euler Discretization, which is something we have already seen in this course. where the discretization is very much straightforward. Often it's also considered to be quick and dirty approach. This means that once you have an SDE, you just follow the Euler discretization, and in a very short period of time, you will have results. This is, although very popular way and the simplest possible way you can imagine to simulate SDEs, it has also some limitations. It's often considered to be problematic if you have high dimensions, and convergence strongly depends on the size of your time steps. So this means that the convergence will be achieved if you have many time steps. So that's so there is always something for something. You can get simplicity, however, accuracy and the speed, those are the limitations. So we start with a stochastic differential equation. However, here I consider this just a one-dimensional case, but the same approach will hold for the multi-dimensional cases. And this is something what we have already seen in Euler discretization. Whenever we have a D, so in a discretization of S, and of course here, we perform kind of Ito discretization. You can also think like this. So we have Si plus 1, so I indicates time step, so the next time step is equal to Si. Of course, this will be exactly, this comes from this point, so we have here Sti plus 1 minus Sti. If you move this Sti to the other side, this is exactly what you have. Then we have a mu Siti, so we evaluate this one at this point, the previous point, times delta t. Then we have a sigma Siti, so you can see it here. We can also dependence on S. So this also means we don't need to do any log transformation. We can just directly apply Euler discretization to this geometric Brownian motion, or even much more complicated SD. It doesn't really matter. And finally, we have a Brownian motion, so it's a delta Wi. And this is delta Wi. This is something we have already discussed earlier. Maybe one thing you will notice here, that this is not necessarily true. Here should be D. So this means there is equality in distribution. It's not the same as equality. So here are the independent increments. And so to simulate that, we have samples from standard normal and then the square root of delta t. So this is, of course, this works once we define certain grid. So we do discretization at the time, and then we can just perform this simulation. Then we have an error definition. So this is related also to the strong convergence, where because now we will be performing simulation, we would like to also to measure the strong and weak convergence. For that reason, we use the measure of absolute error, which is an expectation. And as you can see, it's absolute value of difference between S at maturity minus ST, so also the maturity, but depending on age. And age is our grid size, so it's a mesh. So bigger the age, we would expect lower quality results. So now we have to vary that. What is also important is that you can imagine that this equality, this is something we already discussed in this lecture. It is a pathwise error, right? So we look at the path level. So you have to make sure that in both cases, so ST and minus STH, they have exactly the same Brownian motion. I hope this will be in a few maybe minutes clearer, but this is important that the randomness in both variables are the same, because if you just simulate ST with some, let's say, million paths, or this is just a distribution, then you simulated some STH. But whenever you will get the new paths, then the error, those paths are not really comparable. So you have to make sure that the random generator for both, for exact and also the discretized version, is the same. And that, I hope, it will be clear in the next few slides. Okay, this is a little bit more detailed. So once we consider not only, because in this case we have a time step, right? But I already mentioned that in the simulation, typically we consider vectors, right? So it's for every time step, Si essentially here will be a vector. So we will have a vector. This will be for Si plus 1, 1, Si plus 1, 2, and so on. So typically, I don't write the second index. We always consider, if we think of Monte Carlo, always vectorized. Never use double loops for a time step and paths. That's extremely expensive. So this is the shorthand notation, you can say, of a vector for all the paths. However, if you like to write it down in a path level, so you have a time step and also J indicates the path, this is what you would have. Now, once we talk about the comparison and the strong convergence, we need to think, okay, how do we would get our exact solution before we discretize? So for geometric Brownian motion, so here we have a particular case of a process that we are analyzing. So we have a geometric Brownian motion with R and sigma. We know that exact solution for this process, so we know from Ito's lemma, we already have it discussed earlier, that every time step, so it's a STI plus 1 and STI, and we have this as the solution that we have. So you see, essentially, you can say that this representation is exact simulation. This means that in order to make a time step from Ti to Ti plus 1, we don't need to have intermediate steps. We have explicitly the relation between any Ti's and Ti plus 1. So this is exact representation, and this is the quantity that we are going to compare to our discretization that we get from here. And what is very important is that this Brownian motion that we generate here, it's also is the same Brownian motion as we use here. So you see here in exact representation, we will be first simulating Brownian motion. We will be using exact representation and using the same Brownian motion in the approximation, Euler discretization. In that way, we are able to compare path by path because we know that in both cases, we have the same randomness, which is driving exact value and also approximation. So if we define some parameter sets, so it's S50, interest rate 6%, volatility 30%, and maturity 1, then we can determine the strong convergence as follows. So here we basically apply, essentially we apply just definition of our strong convergence, the absolute error, which is defined as average, so it's 1 over n is number of samples, and then we have summation over all the SIT, so essentially every path that we get from this quantity at time t, so this will be SIT. So for every entry in our vector, this is what we have here, minus sample that we will get from this discretization. You see it's a M indicating the last time step of our simulation and J indicating path. So this is the comparison. Essentially, this means that we compare these two things. We compare discretization and exact. And once we simplify, we substitute the definition of STI plus 1, and this is what we get. We get the summation, and then we have exact representation minus SMJ, and this is the one which we obtain from the Euler discretization. Now, if you would like to measure the error in weak sense, so weak convergence, it is slightly different. So we see error weak, W, which depends also on delta t, or often we indicate it by h. And then we have an absolute value of averages. So you see that's a mean value of the exact samples minus the average of the samples that we have obtained from Euler discretization. So we can again substitute, but as you can see, it doesn't really matter anymore whether the Brownian motion, which is here and here, they are kind of put together. We are not interested whether the Brownian motions are the same. We are only look at the average error. So basically, average, we put everything together and we calculate average and we see whether this error is big or small. So that's, of course, it's a weakened convergence and weakened quality of approximation. Like I mentioned before, once you talk about the pricing of a European type of payoff, weak convergence is often sufficient because we are only interested in the payment at one given time. However, if you talk about path-dependent payoffs, then weak convergence definitely is not enough because this error, although maybe very small, could be very big if we look at individual paths. So this means that this approximation could give you, although highly accurate for given maturity, could be definitely different if you talk about transition densities and path dependence. And here one more time, very important to keep in mind that if you look at errors, especially in the strong sense, you have to use the same Brownian motions. This is a key element. In a few seconds, I will show you how to perform simulation of that, so that will be very clear how to implement this kind of the same Brownian motion and use it in both approaches. This is the result that we have obtained for Euler discretization. So strong convergence, you can actually see here, maybe let's take a look at the first graph here. So here are the paths, generated for the Euler discretization compared to the exact solution. So you see that initially you cannot really distinguish the differences. However, if we go further in time, for some of those paths, the differences are maybe not huge, but you can see there is an error, there is a difference, right? On the right-hand side, we have a comparison of a strong and weak error. So red line indicates the weak error. So you see, because we put everything together, the error typically is smaller because we don't look at the individual paths. For strong error, you see it behaves like a square root of delta t or square root of h. And this is what we actually say about the convergence. The Euler scheme is convergent as a square root of t. So this is something to keep in mind. Okay, now let's take a look at the code, how to implement this. So in this code, we have again two blocks, the main function where we specify configuration of the model, and we have the second part, actually is the core, which generates the paths. So you see here we have a maturity of 1 year, 6%, volatility we have chosen to 30%. We have a path where we generate just the paths. So this part of the code will only generate the figure. So if we just run this, here, this is the graph that we obtained from the first part of code. However, this is not very much of a value, right? In terms that you can look at this, it tells you that it looks quite okay, but you cannot really quantify it. To quantify the error, we really need to use the measure of error, which we have discussed just in a second in the slides. So for the weak and strong convergence, we define as follows. So we have we define a range of number of steps. This means that we have a maturity of a year, 1 year, and by number of steps, we just divide it by a certain number of steps. We can do 1 division, we can have 2 intervals from 0 to 1, 3, and so on. And then for each of those steps, we perform Monte Carlo simulation, for which we will compare exact versus approximation. So let's go to the function. So this is generate paths GBM Euler. And what we do here, we first define samples. So we know that we have certain number of paths and certain number of time steps. So this is paths time steps. So we have a big array. Then we have empty vector metrics of Brownian motions. We define also zeros, empty matrices for approximation exact. I already have mentioned before, it's always good to keep objects like matrices, predefine them and make sure that they're empty. And then what we do next, we first generate Brownian motion. So this is what we do here. And here we have 2 stocks you can think. The first one is Euler discretization. So we have S1 at time I plus R. And then you can see it is just the Euler discretization as we have just discussed a second ago in the slides. And on the other hand, we have exact representation, which is also given in the slide. So this is exact formula for pricing of simulating of geometric Brownian motion. So here maybe it's a sigma times sigma. Pythonish would be sigma squared. And the most important element, like I already also stressed before, is that those Brownian motions in this case and in this case are exactly the same. Then we can compare them at the error level. If we wouldn't have this, then those paths definitely would not be even close to each other because those would be completely different random numbers. So we cannot really compare strong convergence. We can still look at the weak convergence that would be not unchanged, but in strong convergence that would have no meaning. Okay, so those paths will be essentially, those are outputs. The outputs are time paths for stock first one and the second one, which is the exact. And once we have that, we define 2 errors. You can see that we are looking at, we take S1 and S2, so we take stocks from stock value from Euler discretization exact, but we only measure the error at the maturity. So this is what we do. Here we extract stock from outputs that we have generated here. And here by this index, we say we take all the paths. So it's the first index corresponds to paths. And we have -1 indicating it's a last column. This means it's a payment at the maturity. It's exactly what we want because we are measuring, we have defined the grid from 0 to 1. So we always look at the value at time t1. So once we have S1 and S2 at time t, we can define 2 errors. The first one is a strong convergence. Actually, sorry, the first one is a weak because we take absolute value of a mean of a stock at first stock at the end minus mean of the second stock at the end. And for the strong error, we take mean and then we define absolute value. And then inside the absolute value, we subtract these two vectors. And once we run it, let's see. Actually, it's, now this is the previous result. Let's see it again. Of course, this will be, as you can imagine, it's not super fast because the simulation has to be repeated many times because you see it's a range from 1 to 500. So it's for one division, for two divisions, everything has to be simulated. So that could be very time consuming. So those again are the paths for strong and for the paths for generated from Euler versus exact. And here we have the final results. This is the error. So the blue line corresponds to the weak convergence. It's slowly growing, and we have a square root of delta t for the strong convergence. You see, it's this doesn't resemble maybe the picture that we have seen in the slides. This can be achieved if we have higher number of paths. Let me do 250. Hopefully, it will still manage to do it within a reasonable amount of time. Let's see. It will be at least 2.5 times slower. You see, once we increase number of paths to 250, the quality, we have seen more and more of this type of square root of delta t shape. So this confirms our analysis. What does it actually mean that the error that we observe is a square root of delta t? So we have this kind of shape. How to interpret that? If we look at this equation here, inequality, we have a strong convergence error of delta t is less or equal constant times square root of delta t. And what it says is basically as follows, is that if you like to reduce our error by 100, because we have a square root, this means that delta t has to be changed by 10,000. So this half here, it is a problematic. We would like to have a convergence where this half does not exist. So for example, if we have a order of 1, then this half basically would be gone. And then if you like to reduce the error by 100, your delta dt will need to be reduced by 100, so which is nicely proportional. If you in the case we have a square root, then indeed we need to make a square of the error that we would like to reduce. So 100 reduction of an error cost us 10,000 smaller time step. And obviously, once we think of a reduction of a time step by 10,000, this means that this will directly translate to our computational time needed for the modeling, for the evaluation. In the next block, we will be talking about the Milstein scheme, where actually the order is of 1. This means that we can significantly improve the convergence. A simple extension to Euler's discretization is the Milstein discretization. Milstein discretization is very much similar to Euler, except that it involves additional, let's say, correction term, which is included in the discretization. The technique is derived by applying Taylor's expansion. We call it also Ito-Taylor expansion. So as you may remember, in Ito's table or Ito's lemma, we had to compute second order derivatives. However, if we include additional terms, those terms can be used to enhance the discretization technique. So let us summarize here. The details on those derivations you can find in the book. There is a little bit of work to arrive at the final formula, but here I will just concentrate on the final results that you can apply. So if we talk about Euler discretization, we have essentially initial point. So we have step ti plus 1 is equal to the value of fi, and then we have two elements. We have a drift and we have a diffusion part. Milstein discretization involves additional third term that needs to be included. You can see there is a half of sigma w squared dt minus dt, and then we have a derivative of a volatility term with respect to state variable x that is included. So essentially, once we have implemented Euler scheme, we can simply add this additional term in order to switch from Euler to Milstein. Of course, everything depends on availability of this derivative. And Unfortunately, it happens that in this technique, not always this derivative is derived or is available analytically. So in a geometric Brownian motion scheme, you can see here we have a mu equal to Rs, we have a sigma, so this is just a standard setting. So Euler discretization would be Si, and then we have a part for the drift. We have a volatility times the increment of Brownian motion, and then we have this additional term, which is half of sigma squared Si, and then we have a Brownian motion. So as you can see here, we have a sigma txi in a geometric Brownian motion case. This term, it is simply equal to sigma times s. And this term, of course, this is the whole volatility that we have to differentiate with respect to underlying variable. So we differentiate sigma s with respect to s. That means that the final, the volatility term, this term plus this term, or times this term, it will be sigma squared s. And then we have one more term left, which is here. So you see we have a half of sigma squared s, and then we have terms only dependent on a dt, and we have a square of Brownian motion. So in a diffusion, in the distribution sense, we can, this is the same as Si. Then we have a drift, just like in Euler scheme, we have a diffusion part, and then we have additional correction term, which is half of a sigma squared Si, and then we have a standard normal squared, samples from a standard normal, minus delta t. This technique, actually, in this case, can be applied also for more processes, but unfortunately, the derivations of this derivative, it's allowed only in closed form for rather simplistic methods. So if we have models involving multi-dimensions, where volatility involves also stochastic volatility or even higher dimension, then this derivative could be very difficult to derive analytically. And in that cases, the benefits of a faster convergence, they are kind of lost because this derivative may require that some additional computations need to be performed. So like I just mentioned, in high dimensions, it is it's far from trivial. This is the implementation. We will look in a second into code. The same as for Euler scheme, we have some settings for the model, and then we observe paths. You can see they are much closer to the exact. So in this case, the same as we have done for Euler scheme, we compare exact paths versus the approximated paths. But with this additional correction term, we see that the paths are much closer than they used to be in an Euler scheme. And here the error for the weak sense, it resembles the same as for Euler, but for a strong sense, we see it is it's linear in dt, so we can say that the absolute error is of order delta t. So like we have discussed already before, the advantage over Euler, of course, is that if you like to reduce our error by 100, this means that our delta t has to be reduced also by 100. In an Euler scheme, if you like to reduce error by 100, we need to reduce the size of the grid by 10,000, and that's significantly different. Let's take a look at the code. So here you can see it is basically, essentially, is the same piece of code we have seen already in the Euler case. Configurations, generations of the paths, and analysis depending on a division of the interval from 0 to time t. So let's concentrate here. Let's take a look at how those paths are generated. In the first case, we have this is the you can see it is almost the same as this part is the same as we had for Euler discretization, and we have this correction term which is half sigma squared. Let's do it here better. Sigma squared times s at every time ti, and then we have this additional correction where we say it should be Brownian motion, the increment of Brownian motion squared minus dt. And this is this additional correction term. S2 is essentially the same stock, but simulated and is simulated with the same Brownian motion. However, here we use exact solution for paths. In this way, we can compare the strong convergence. We need to always, to talk about strong convergence, we need to know exactly how this distribution behaves for each individual noise. So that's the element here why we are looking at this exact solution. Keep in mind that for not always for all the processes you'll be able to find this exact solution, and also keep in mind that once you have this exact solution, for example here in this line 35, we know exactly how to make those large time steps. This means that in essence we don't need either Euler or Milstein. Those are really useless because since you know the distribution at every time step, you can just call it. You don't need to simulate. You don't need to discretize. Maybe you can think of small time steps in a path-dependent payoff, but once you have exact solution, this formulation in line 35 allows you already to do any time steps you wish. So in here, you can think that the analysis we have done for Euler and Milstein scheme, it is more for illustrative purposes to show you what is the impact of different discretization techniques on convergence on example of black shoals or geometric Brownian motion. So let's just perform the run. So here we do 100 paths and we measure the convergence from a time interval divided by from 1 to 500. This is what we do. And as we have seen before already, paths performing, they're very close to each other, so exact versus Milstein. And here we have an error for weak convergence and strong convergence. Of course, those lines become nicer once we have a higher number of paths. So it's, of course, the zigzags here that we see, this is associated with the insufficient number of paths. Let us go back to the slides. And I think I have prepared one more picture, one more slide, where we compare errors for given maturity time t between Milstein and Euler scheme. So on the left-hand side here, we can see this is the error that we will have for each individual path if you just look only at the differences between vectors for exact versus Euler. This is a distribution of error that we can see. And on the right-hand side, we have the same distribution, but for Milstein scheme. And I kept the range to be the same, so minus 10 to 4, minus 10 to 4. You can see the Euler approach, Euler discretization, the error is much higher. For Milstein, you can see it's concentrated from, let's say, minus 1.5 and half or 1. Here we have error still from minus 6 to 2.5 or so. So there is a big difference. Of course, Milstein scheme is not always applicable, so keep that in mind. If you have a problem with discretization or the speed, Milstein indeed can help you, but only if you're able to derive the volatility coefficients or those derivatives analytically. If you like to do it numerically, I would say that this could be computationally also expensive. So the benefit of using different scheme may not be seen once you look at the final results, and not only about quality, but also when we look at the error that you generate. And of course, the time. This is also important. Always keeping time in mind. Later, we will be discussing exact simulations of processes. So like in a Black-Scholes model, in the geometric Brownian motion, we can make large time steps. And this will be very important once we talk about fast simulations of Monte Carlo, where we don't need to look at the discretizations, especially if you are only interested in only particular dates on the grid. Then small time steps in between only make this simulation very computationally expensive.